The next section is predicates and quantifiers. So when we talk about predicates, we also talk about the subject. As in an English statement, you know that you have a subject and a predicate, and the subject is going to perform some action on the predicate. In this case, in this example, we have x is greater than 3. It has two parts, and then so we have x is the subject, greater than 3 is the predicate. To denote this using mathematical symbols, we're going to use p for the predicate, and x is going to be the subject. So, and we read this as p of x. So let's take a look at going back to our regular example. Toronto is the capital of Canada. So x would be Toronto, and p is the capital of Canada. So if x is Toronto, y is Ottawa, then you have that p of x is false, p of y is true. Let's take a look at quantifiers. By many times, what you want to do is you want to find kind of a shortcut way of saying something about a group of things. So we have the universal quantifier that will say something about everything within that within certain context. So we use this symbol to say for all x, so that means that every x, okay, and then we use a predicate, and this symbol can be read as for all, for every, for any, for each, given any, or for arbitrary. You can read them the way you like them. In some scenarios, one ways sound better than others, but ultimately they all mean the same. So an element for which this predicate is false is called a counterexample of the universal quantifier for that predicate. So the counterpart of the universal quantifier is the existential quantifier. It is kind of with the universal quantifier, you say something about everything within that context. With the existential quantifier, you say something about a particular element that belongs to this context. I can say, in this case, if the predicate is the capital of Canada, then I can say there is a city which is the capital of Canada. To denote that in mathematics, we use the inverted E or mirror E symbol. And you can read that as there is, for some, there exists, or for at least one. Every time you use the existential quantifier, you have to specify a domain. The existential quantifier by itself may be meaningless. It all depends on the context, but normally you need a domain. So let's take a look at domains and how you can restrict the domain of a quantifier. Here we have a very simple statement that says for all x less than 0, x squared is greater than 0. So that's kind of a shortcut way of saying that x is less than 0 for every real number x such that x is less than 0, x squared is greater than 0. So there are some relationship between the universal quantifier and the existential quantifier, and the restrictions that you can apply to those. So the relationship is exemplified here. You have for all x less than 0, x squared greater than 0. This is logically equivalent to saying for all x less than 0 implies that x squared is greater than 0. Okay, so here this is going to help you when you are trying to solve or trying to analyze a statement, a logical statement, and you want to simplify it, or you want to expand it perhaps, and then analyze smaller parts of it. This will become very handy. So what happens when you negate quantified expressions? Let's take a look. You can negate that for all cities, all the cities are capital of Canada. The negation of that would be there is no city that is a capital of Canada. Let's take a look at this concrete example we have here on the screen. It says the negation of for all x, p of x, is there is an x such that it's not the case that p of x. And then you have the negation of an existential quantifier, and that is equivalent to the universal quantifier with the negated predicate. Okay, so we have these two cases. The negation of a universal quantifier is equivalent to the existential quantifier with the negated predicate. The negation of an existential quantifier is equivalent to the universal quantifier on the negation of the predicate.